And it's maybe why I thought that the Java class had discussed overloaded functions, because we did in C++ or vice versa. So anyways, an overloaded function is when you have functions with the same name but different parameter lists. That way you can create a function that performs the same task but it takes different parameter types. You might write a function that adds 2 ints, and you might write another one that adds 2 doubles for whatever purpose. And then the compiler determines which version of the function to call. So a quick example of that, and I'm not going to even have y'all type it in, would be you might write a function that greets somebody. And so it's going to take somebody's name. And so it couts hello, followed by their name, followed by an exclamation mark, right? Then you can make another one, because not all people just have one name. What if you want to be able to pass in a first and a last name? So you write a second function, fname, string lname. So this one takes 2 parameters. So you can pass 2 arguments to it. And it says hello, prints out their first name, followed by a space. This looks like a test question. Followed by their last name, followed by exclamation mark, \n. And you could write a third one that took a first and a middle and a last name, right? Same kind of idea. Void hello has a first name, fname, has a middle name, mname. Did I use this example last time? This is seeming real familiar. No, maybe not. And then string lname for the last name. And you just use all 3 of those in your hello. Hello, followed by the first name, followed by a space, followed by the middle name, followed by a space, followed by the last name, followed by a exclamation mark, \n. So when you're ready to call those down in main, you could just do a hello Bob. You could do a hello John Roberts. Nope, but it takes like that. You could do a hello John Quimby Roberts, like that. You can call it with 1, 2, or 3 functions. You have overloaded that function. There are several different versions of the function, and which code gets executed is based on the arguments. The compiler hooks up the number of arguments and the types of arguments to the declaration of the header of the function that matches, and you're good to go. So when we write this code, the compiler goes, oh, you need a function that's called hello, and it has 3 strings. Aha, there's that one, hello, and it's got 3 strings, so we're good. And if you call it with 2 strings instead, it says, okay, I need to find a function called hello that accepts 2 parameters that are both strings. And so inside its little internal mapping, it finds a function named hello that has 2 strings as parameters, and it invokes that one. The other example, the one that I give quite often, is an add function. Int add I1, int I1 comma int I2. And it's just going to return I1 plus I2. Then you could write a different version that took 3 numbers. Int add, give it the same name, just make it easier to use. Int I1, int I2, int I3. Return I1 plus I2 plus I3. Like that. Why do that? So that you can use the add function and not really care about how much data you're passing to it. You'd probably give it a third version that accepted 4 of them. Int add1, int add2, int I3, int I4. And so it's going to return I1 plus I2 plus I3 plus I4. So when you were ready to use it, you could cout add 1 comma 2. That's going to write out 3. You could cout add 10 comma 20 comma 30, and it'll call the one that accepts 3 arguments. You could use the one that accepts 4 arguments. Like that. See, and it's kind of nice. You can just use the same function. We didn't have to write one that was called add2, because I wanted to pass 2 parameters to it. And add 3 if I wanted to pass 3 parameters to it. And add 4 because I wanted to pass 4 parameters to it. That kind of makes a limited kind of sense too. But what if what was changing was not just the data type, not just the number of parameters, but their type? You might want the ability to add strings together as well. So string add, and it takes string S1 and S2. And it's going to return S1 plus S2. So if you called it like this, string name is equal to add Bob and Roberts. Not a real good idea because it's not going to have any spaces in it. But anyways, so now we have a function of add that takes 2 numbers and adds them together. And we have another version of the add method, function, that accepts 2 strings. And so if we'd been kind of going with that idea, I'm going to just call every one of these a different thing. We're back to being add to, add to S. Why not just make them all have the same name and accept different data types? You want to write another version of add that takes doubles rather than ints? Yeah, you can do that. You want a version of add which will take 3 strings and 4 strings and concatenate them all? You can do that. You want to write a version of add that will accept an array of values, which we haven't talked about in this class, then you can do that. Somebody's missing. Olivia. All right. So anyways, that's overloading. Overloading is when they have the same name but different parameter lists. Close, dang it. All right. So you can use it to make functions that perform the same task but have different parameters. The compiler figures out which version to call. So here we have created something called get dimensions, and if you pass in one number, it's a one-dimensional value. Get dimensions, but if you pass in 2 numbers, it's a 2-dimensional value. Get dimensions 3 numbers. Well, int double is a 3 for some reason. I don't know what we're really doing that for. But anyways, so we've created the same method name that behaves differently based, same function name that behaves differently based on the parameters passed in. The exit function. We've seen the return function. Exit's kind of like it, except it kills your program. Stops it. Return just leaves a function, right? But exit kills the whole thing. So you could write a function that looks like this, right? I'm going to take something that called multiply to, and it takes in 2 numbers, int a and int b. It calculates the result. Int result is equal to a times b. And then you do return the result. That's great. So down here you can call that inside a main, blah, blah, blah. You do cout multiply 100 by 5. And it should print out 500. But there's the word exit. It's a keyword that would actually kill the program. It stops it at that point. So you could write something called divide that takes 2 values, int a and int b. And this would be a horrible way to write this function. But you could declare a result, but we don't want to ever divide by 0. That's a problem. So we're going to have the great idea of saying if b is equal to 0, print out an error message and exit. That's stupid, right? But anyways, else, we don't even need an else because I'm putting an exit right here. I think I have to put a number between them. Let me eyeball the... Yeah, you pass an int back to it. you're passing a value back to the operating system that called the value, the program, just like the return at the bottom of main does. So then the result is equal to A divided by B. We're going to return result. Now we're done with that function. So if we come down here inside of main, first we did cout of multiply by 2. Now we're going to do cout of divide 100 by 0. What it does is when we called multiply by 2, it ran up here, did this line of code. When it hit return, it passed that value back, so it could be used here. But here we call divide, passing in 2 arguments, 100, 0. It runs up here. A gets 100, B gets 0. If B is equal to 0, we write out error, and we kill the program. The process terminates. Your program goes away, and the operating system, if it called it, gets a 0 back in its little buffer, just like the return statement. So typically what you do is if you're going to use the exit statement, you return non-zero error codes, and you make each one different. Error code 1 might mean divide by 0. Error code 2 might mean file not found. Error code 3 might be this. And that's really old school programming, but Linux, Unix type folks do make use of return codes from programs, whereas Windows doesn't. Who's launching the application? You are. You're double clicking the app, and it's not like it. Once the app closes, it displays a little 3 in the corner of the screen saying you had error code 3. You just don't see that, even if it did. So that's what exit does. Kills the program, whereas return leaves the function, returning a value back to the calling function. And in the case of main, the final return down at the bottom, like that, works the same as an exit statement because main has nothing to do after that, right? It's at the end of the program. It's bailed out of it. So, but it's better to do a return. I won't say it's better. Doesn't matter. Okay. So to use the exit function, you have to include C standard lib. Use it very, very sparingly, if at all. Honestly, I never used it as a professional programmer because you try to make your program handle errors rather than just give up. C standard lib comes with 2 constants that are already defined. You could use these. Exit underscore success and exit underscore failure. Success is probably defined to be 0, but it'd be kind of fun to find out. So let's go ahead and load up Visual Studio. And the only reason I'm doing this at this point is because I want to find out what those error code values are. But also, any moment now we're going to probably actually start writing code. String.
What is string buff?
Don't know.
Oh, that's it.
Then C standard lib. Downsign includes CMath. Why is this yelling at me? No, okay. Using namespace std int main return or pause. System pause, return 0. So I'm going to write a function called goodbye, cruel world, or fail. That's all I'm going to call it. Void fail. And all it does is it calls the exit function. Exit with that value. Exits failure. Exit underscore failure. So if I wanted to, my code could call the fail function. If I do that, it's not going to even get to that pause, right? So when I run it, we're just going to see it launch and immediately go away. It may go that so quickly we don't even get to see it happen. Yeah, boom, it's gone. It never reached pause because it ran this function. The first line in the function was just a call to exit, which terminated the program. So now I'm going to right click on exit failure and go to definition. And yeah, that's what I thought. 0 for success, 1 for failure. That's just a convention that people have decided upon, that if your program returns 0, it means everything was hunky-dory. And a non-zero value is supposed to be an error code, and you can give whoever's developing with your program a list of error codes. Stubs and drivers. A stub is a dummy function used in place of the actual function. Usually displays a message indicating that it was called. Might also display its parameters. And a driver is a function that tests another function by calling it. So, you might do this. I'm going to write a program that multiplies 3 numbers together. So, double mult, double D1, double D2, double D3. And you go, you know what, I don't really know how to make that work. So I'm just going to print out a message that says mult called. \n. And then down in my code, I'm going to take the call to fail out. I'm going to comment it out. Down in my code, when I'm ready to multiply something, mult 1 times 2 times 3, is it going to really do anything? No, it's just going to print that mult was called. But then we'll go back in and we'll fill it in with good code. I forgot to return something. This is defined as having a return type, so the function does have to have a return statement that returns something of that type. 0 works. So it runs and it says mult called. And that's all it did. And then later on I go in and I actually fill in what mult does. And I take that little print statement out. And you use that when you're kind of sketching out your program. Like when you're going to write a paper for an English class and you have to come up with your opening body and then 3 more bodies and then a conclusion. 3 more paragraphs and a conclusion, so you can kind of fill them in like that. You might write something that kind of looks like this. Void get input, and all it does is going to say get input called. And then you might write another one called void process data, and we're not going to go back in and actually write this stuff in, and what it does is it prints out process underscore data called. And so then down in our code, when we're ready to start coding based on those things, our first call could be to get input. Our second call could be to process data. The idea is you can flesh out the structure of your program very quickly. Now, not all the pieces have to do anything. But it lets you lay the structure down, and then, then you can go back and you can figure out how you're going to get your input and what it's going to be stored as. And you can fill in all the code that's associated with that. And once you like the way your program gets some input, then you can decide what process data is going to do. Hopefully you kind of know before you start writing the program right. But anyways, so then I decide that what process data is really going to do is it's going to call our mult function. That's its purpose in life. So double D or answer is equal to multiply 1 times 2 times 3. Now it's actually implementing what it's supposed to do, so I comment that out. Now when I run it, I don't see that message anymore about calling process data. It just says mult called. Then I decide that I know what get input is going to do. It's going to ask them for a number. So cout, enter a number, int x, cin into x. All right, now that function's done. I'm going to comment that out. I'm going to comment the print statement out. We don't need to do that anymore. We don't need to say get input called anymore because we've actually written the function. You can leave those debug messages in for a while. Eventually, though, you're going to take them out. So now when I run it, it's not going to say have that get input message. It's actually going to do something. Enter number 20. But we still have one stub left. The mult function hasn't been filled in. I'm going to go back and fill in the mult function now. I'm going to go here. I'm going to comment that out, and I'm just going to return d1 times d2 times d3. Now when I run it, I don't get any of those extraneous messages. Now, does the program really do anything? No. But you get the idea. I fleshed it out. I kind of mapped out its skeleton, and then I went back in and I filled in each piece one by one until it started doing what I wanted it to do. All right, and I promised myself that I wasn't going to keep going on until people got lost, like I have recently. So we made some changes while it was paused. Forgot to unpause it. So here we added this up to the top of the program. Namespace, our data, curly brace, int value equals 0, semicolon, end curly brace. Then we went down here to our functions and we used that value, that new global variable. So here's the line that we added to the get underscore input function. Pause the screen, make sure that you make your get input function look exactly like this one. That's the line that we entered. That was the change. Same for process data. We made significant changes to that one. This is what the process data function looks like now, those two lines of code. Then we added a third function called show result. Cout, our result is our data : value ENDL. And since our program wasn't calling show result, we went down, took out the call to mult, and instead added our show result there. And when you run it, you type in a number and it displays the cube of that number. And our number for 64. All right, so now you're caught up. We're all good in here. When I ask, really stop. Don't wait.
One line, please.
All right.
Line 2, 3.
Further?
No.
Okay, okay. Got a question?
Whenever you put using namespace std, earlier you said professionals don't do that, so they don't put std colon.
Exactly.
Whatever.
Right. If we were pros, I wouldn't be putting this on here. I would make us type std : everywhere throughout the program.
So now you have namespace our data.
So we could, yeah, we have namespace our data. So we could, if we wanted to, do using namespace our data.
Now there's no need for the our data.
And now we don't need to put our data : everywhere. So if we wanted to, we could just say value, is equal to 3 or whatever.
Is that something people would do?
Yeah, absolutely. Absolutely. If you define your own namespace that's specific to this program, there's absolutely no reason. I was just making us type it that way to burn in the concept of the namespace, to make it painful. Okay. The driver is a function that tests another function by calling it. Various arguments are passed in and returned. Values are tested. So we have a multiplier function, a mult function. We might want to test it out. So we might write something called test mult. Void test underscore mult. I'm going to do this. Int x1 is equal to mult 10, 20, 30. Int x2 is equal to mult 0, 0, 0. Now we know what those two things should be. We could just display them, or we could double check to make sure that they're working. If x, what is x1 supposed to be? 10 times 20 is 200, times 30 is 6,000. So if x1 is not, why didn't I pick easier numbers to multiply in my head? But anyways, if x1 is not equal to 6,000, then let's fail. I don't think, like that. We ought to print an error message out first, though. And then if x2 is not equal to 0, because 0 times 0 times 0, then fail. So we're writing a test function. And like I said, these should be printing out information about it. So that we know which test it failed. Test mult is a driver. It drives our multiplier function, exercises it, works it out, tests it. Our Java textbook in the Java class uses the term driver for something in a different sense. It means the client of a class. Just get used to the idea that textbooks use the same word for different things, unfortunately. There is a short form of this called the assert statement. And let's see if they mention assert here. I don't think they do. C++ assert. Here's what assert does. That's not telling me much. Here you go. You run your test, but you put it inside an assert statement. And so let's do that. We're going to come down here back to our driver. And so we're going to assert that x1 equals 6,000. Do we really have to include something for assert? Bah humbug. Include C assert. Okay. Go up to the top. We're adding another one. # include C assert. So get that in there. # include C assert. Now go back down to our driver code, which was called test mult. We're going to assert that x1 was equal to 6,000, and if it was, we're going to say passed x1 test, and then we're going to assert that x2 is equal to 0. And if that doesn't fail, then we're going to see out passed x2 test. And you only use asserts for things that you are sure are going to work, and if they're not going to work, it needs to kill the program. It's a debugging tool. You don't put it in production code. If you compile for production release rather than debug release, and so far we've been, compiling everything for debug, but you could compile for release rather than debug, then the asserts don't do anything. They're just for debugging purposes. If this is true, great, nothing happens. But if it's false, it kills the program. Let's run it and see if we can see witness to that happening. Well, it's not going to fail, is it? Enter number 1. Our result is 1. But let's introduce a bug into our program. What is our bug going to be? If D1 is equal to 0, return whatever. 1, 2, 3, 4, 5, 6. It's a horrible bug, right? Just because you're multiplying something by 0 doesn't mean that you ought to be returning 1, 2, 3, 4, 5. So it's going to pass this test, but it's going to fail that one. So when I run it, I never actually called the test mult function. I need to go put a line down in main that's going to call test mult. We've written it, but we never used it. I'm going to cut that and paste it so that it's right above main so that we can keep it on the screen as long as possible. Yours isn't in the same place probably, but that's okay. So at the top of main, I'm going to call test underscore mult. See that? Why? Because it's running our tests, making sure that they work. Right now we only have one function that performs a calculation, but if we had other functions that performed other calculations, then our test function could test those as well. And it says debug error. Program R6010, abort has been called. We see that it passed the x1 test, but then it says assertion failed. x2 equals 0. It's telling us what went wrong there. x2 was supposed to equal 0, but it didn't. Then it's up to you to go and debug the code. You could click retry. Hopefully it would pull up the debugger, and we could take a look at what line caused it. Now I'm going to stop debugging. I guess it already has stopped. Okay. So that's what the assert function does. I'm now going to go remove that bug from my mult function because I don't want it to keep doing that. I'm going to take that if statement away. That was just to demonstrate the assert. So what assert does is you put an expression in there, and if that expression is true, nothing happens. Everything's A-OK. But if that expression is false, it kills your program and offers to bring up the debugger so you can figure it out.
Can you scroll down a little bit?
Like that? You need it further?
No, that's fine.
Okay, okay, cool.
So once the assertion fails, it doesn't do anything else.
Pardon me?
If the assertion fails, it does nothing else.
Yeah, once the assertion fails. Well, let's find out. This is an incorrect assertion, right? x2 does not equal 1 after we multiply all zeros. So boom, it blows up. It says that we could click retry or abort, or we could ignore the bug. I swear that ignore killed it as well. I don't see the output from it. Whereas if it had worked, we would have gotten the chance to type in something. But yeah, it essentially kills the program. You can enter the debugger to see what line of code failed, but that's pretty much it. Okay.
What's the real world application?
To make sure the program works, you can litter your code. You know, when you have something that has 700 different functions, and it's a large body of code, and you have a team of programmers working on it, then you go in and you write a whole test suite of tests of drivers for those functions, and you put a whole bunch of asserts in there, and it runs that test suite every time you run the program. And then if somebody goes in and they modifies the code in such a way that the function no longer returns the right value, you know instantly that they've done that. You don't wait until you trigger whatever obscure function was actually supposed to, Like if you never saved your data and you never tested out the save function, then you might not see a bug in it until you actually, did do a save. But instead you're running your tests all at once at the beginning of the program, hoping to get it to fail if somebody introduced a problem, if they changed a function so that it didn't return its expected value. And it's a very common tool, actually. If you're writing code that's going to perform calculations, it's really easy to do asserts to make sure that the calculation you performed is the correct one. Hope that makes sense.
Yes.
Yeah.
Instead of having to go in and try it multiple ways.
Exactly. And that is the end of this. We've seen a driver. It's a function that calls another one. Various arguments are passed in, and the return values are tested. It's kind of funny they didn't tell us how to test it. There are other ways of doing it. You could just print out a message. You don't have to call assert. But assert is assuming that you're running it in a debug environment, and you really want to know that it failed. It's a serious error if your multiply function doesn't work. So you don't want the program to continue running if it's not. All right, that's the end of chapter 6. So going on to arrays. So far, all of our variables have held one value. You hold one person's age. You hold one person's weight, one person's height. You hold the radius of one circle, that kind of thing. But usually, quite often, in programming, you want to keep track of multiple values. Like you're playing a video game, and there are 20 characters running around on the screen trying to shoot you all at the same time. You don't just have one character. You have 20 of them all running around. So you need data structures that hold multiple values. And the simplest of those is the array. It can store multiple values of the same type. So instead of just one int, now we can store 5 integers. You declare them using that. Now that's different from Java, by the way. You Java guys, take note that you're going to have to burn into your brain that that's different. So then, once you're done with that, you can start putting data in it. You can say, okay, I want the first value in that series to be 300. I want the second value of that series to be 450, and so on, up until you have assigned 5 values. Since it starts counting as 0, your 5 values are 0, 1, 2, 3, and 4. So this index value here can go from 0 up to 4, or 0 up to the length of the array minus 1. You declare the array to be 100 elements long, you go 0 out to 99, because the range 0 to 99 in zero-based indexing is 100 elements long. So you do that, int tests 5, and out in memory, each int takes up 4 bytes. It's a 32-bit value. We talked about way back at the beginning of the class. So it allocates 20 bytes to hold these 5 integers. That's what that does, is it declares room for 5 integers. The first element, second one, third, fourth, fifth, if you were going to number them, that's in element index 0, element index 1, element index 2, 3, and 4. So when you're declaring your array, the first word is the data type. That's the name of it, just like we normally do, int tests, except now we're saying, oh, but I want 5 ints. That's the size declarator. Now here is where this textbook drives me nuts, because they use this term size in 2 different contexts. They say, okay, that's the size declarator. It's got 5 elements in it. And oh, by the way, the size of the array is equal to the number of the elements times the size of each element. So, firstly, they're saying, okay, it's got an array of 5 ints, so its size is 5. And then they're saying, oh, but its size is really 20, because each int is 4 bytes. There's a function which returns the number of bytes that a variable that a data type uses. And so we'll hit that again. When I refer to the size of an array, I'm probably going to be meaning the length of the array. But that's actually the term I should be using as far as this textbook is concerned. This isn't the size of the array, that's the length of the array. The array is 5 elements long in length, and it's 20 bytes in size. And if it was an array of long longs, which are 8 bytes each, 8 plus 8 plus 8 plus 8 plus 8 would be 40 bytes long. That would be its size. So the size of the array is equal to the total number of bytes times the number of bytes for each element. You can calculate that using something called size of. And it's annoying. Here's where you start seeing that C++ is an older language than some of those that y'all are learning. You're getting your hands a little bit more dirty than you wish you were. So if you have an array that looks like this, int numbers, and it's 8 long, and you want to know how many bytes it is, int bytes is equal to 8 times the size of an int. That's how many bytes it takes up. What if you want to know how long the array is, what its length is? You can't do this, unlike any other languages. You can't do numbers.length. Nope, we don't have that ability. Int length is equal to the size of the numbers array divided by the size of an int. So since an int is 4 bytes long, this calculation would tell us that this is 32 bytes long. But we don't really need that. That's managed by C++. But you do need to know the length of the array. And so, since the size of the array is 32 bytes, if we wanted to get the number of elements, 32 divided by 4 is in fact 8. Man, is it annoying to have to calculate the length of your array by using size of. So what most people do is they declare a constant, and then they just use that constant everywhere. You know, so you could do pound define array size 8, and then you can just use that everywhere where you need it. Inside your while loops, inside your for loops, or whatever. Makes your code easier to read. But that's to make up for the fact that you can't do numbers.length like you can in several other languages that some of y'all have learned. If you want to calculate the length of the array on the fly, that's how you do it. And tragically, it doesn't work in every context. So it's far better to keep track of the length of the array by setting a variable to it. You don't have to do it as a pound sign define, which we haven't been using. You could just do this. Constant int array size equals 8. I'm going to get rid of that one. Not use the pound sign define. And then array size, like that. And then if you ever needed to know the size of the array, you would just reference that variable. You'll get familiar with doing that as we write some array-based code. So named constants are commonly used as the size declarator to declare the length of the array so that you can get a hold of that value later. Constant int size is equal to 5. The length of our array is 5, so they pass in that variable right there. This eases program maintenance when the size of the array needs to be changed. So you're writing software for your cell phone and it's got a smart dial list of 99 phone numbers. And then you're told, okay, from now on I want it to have a smart dial list of 999. And you go into your code and you change the 99 to a 999. Yeah, like that, and it's all good. Gives you one place to change it. Accessing array elements. You start at subscript 0. I will use the terms index and subscript interchangeably. Some books use one term, some books use the other one. This one's using the term subscript. The last element is n-1, where n is the length of the array, the number of elements in the array. Since this array was allocated to be 5 long, then we can do our subscripts 0 all the way out to 4. So tests sub 0 is equal to 79. Once we did that, we'd have a 79 here. Then if we bit back in and we said we let them enter a number for test 1, say that they typed in 42. That's what they typed in. It gets stored into test 1. Now we have the value 42 there. Then we have this test subscript 4 test index value 4 is equal to 0 plus 1. Well, let's go look. Element 0 was a 79. Element 1 was a 42. Why did I make that hard to add up into my hand? Whatever. I'm going to cheat and make that equal to a 21 so that I know that it adds up to 100. Okay. And it would put it out in element 4. So they typed in a 21 there. It stored it in this value. And then this value, test 4, was supposed to be equal to test 0 plus test 1. Hope that makes sense. So you can see it's just like a mailbox, you know, for an apartment complex. You have all sorts of different mailboxes. You put different letters into each one. We put different values into each element of the array. Or if we're spamming in the mailbox, we could be putting the same piece of mail in every single one. So you could copy the same value into every element of the array, whatever. You can access each element either with a variable or like that, or with a literal. Let's write a little bit of code that has to do with arrays now. Let's put it above our test code because, you know, that's asking for input of some kind. So let's declare an array of ints. I'm going to call it IA for int array. And it's going to be 5 long. Let's store some values in it. IA subscript 0. Just type in 5 numbers. IA subscript 1 is equal to another value. IA subscript 2, you don't have to use my numbers, is equal to another value. IA subscript 3 is equal to another one. IA subscript 4 is equal to another one. We used literals to fill in those values. They don't have to be done that way. Usually you won't. Usually you'll probably be using a variable. How about we declare a variable C for counter? Int C is equal to 0. That's our counter. And let's declare another array. It's going to be an array of strings. Array names parentheses 5. Excuse me, string space names parentheses 5. Okay, so names sub C is equal to, and fill in a name that you like. Tony. Now let's add one to C, C++. Names subscript C is equal to Sarah. Now let's add one to C again. And then names subscript C is equal to Bobby. So when we print this out, what's the first element in the array going to be? What is element 0 going to be? Well, let's look at the first one. And I know people are still typing, so I'm going to slow down. What we probably ought to do is write a loop that would print out the values. But we can kind of see. The first element of IA is equal to 71. So IA subscript 0 is 71. The first element, the second element, IA subscript 2 is equal to that number. IA subscript 2, the third one, is equal to 33. IA subscript 3, which is the fourth one, is 42. IA subscript 4 is equal to 1,000. So we have our 5 elements. What does C equal at that particular point in our code? C is equal to 0 at this point. So the first element in our array is the word Tony. Then we add 1 to C. So what is C in this part of the code?
0.
It was 0 here. Then we did C++, so it becomes 1. So name subscript 1 is equal to Sarah. Then we do that. It was 1. Now what is C? 2. So we have an array with 3 valid values, Tony, Sarah, and Bobby. I'm going to change this thing to a 3 rather than a 5. And as a matter of fact, I'm going to do the good thing and declare it as a constant. Constant int number underscore names equals 3. And then I'm going to use that right there so that later on if I decide I want more names, I can change it there. I should go back and do the other one too, but I'm going to skip that for now. Let's write a loop that'll print that out. For int I is equal to 0, I is less than capital num underscore names, I plus plus, C out, I, followed by a space, followed by the names subscript I, followed by ENDL. So it's going to print out all 3 elements of that array. Let's see if it really does. I'll bring the code back as soon as I see that it did. Okay, yeah. That's the most common way of stepping through an array. Iterating through the array, traversing the array. Different books call it different things. Use a for loop. You start at 0, and your while portion is while it's less than the length of the array, however you store that, however you calculate it. And then you access it by that index value. Why am I printing out I as well as the names? I just want you to see those numbers 0, 1, and 2. Because 0 is Tony, 1 is Sarah, and 2 is Bobby. All right. So you can use literals or you can use variables as your index, as your subscript. What would have been an easier way of doing this? Rather than having C++, C++ there, we could have done this. Just put the plus plus right there and then take out that line that says C++. And you could have put in a plus plus right there, take that one out, and put in that one right there, like that. That way we use that value. So 0 is Tony, but C then gets incremented to 1. 1 becomes Sarah, but then that gets incremented, becomes a 2. 2 becomes Bobby, and it gets incremented and becomes 3. And a nice side effect of that is that now you could loop up to the value of C, because C is equal to 3. You'd know how many pieces of data you have put into that array. Because you can have a partially filled array. A partially filled array is one where you have more space than you have data. Like up here, we declared IA to be 5. What if we set it equal to 10? We have room for 10 numbers, but we only put 5 numbers in. It's a partially filled array. The rest of them are 0. Let's write out a loop that will print those out. It's going to look the same. For int I is equal to 0, I is less than. I didn't put this as a constant, so I would have to hard code that there. I should take the time to go ahead and make a constant. Constant int number of ints equals 10. And then I'm going to change my array declaration to be int ia subscript num ints. Then I can use that down here. I is equal to 0, I less than num underscore ints, I plus plus, cout I followed by, let's get fancy, a tab followed by the IA at that specific position, IA subscript I, NDL. So since we declared this to be 10, we're going to see that the first 5 values are non-zero, but then the rest of the array is 0. But it's not 0. I forgot. In other languages that some of y'all are learning about, arrays are initialized to 0. In C++, they are not. They have whatever garbage was left in the memory before it was allocated. So you have to initialize the array yourself to be zeros if you want them to. Fortunately, that's pretty easy. You just add a declarator up here. Alright, so far guys, if you were following along, I changed that, I added this line, I changed this line, and then we added these 3 lines of code. So make sure that you've done that, make sure that works for you. Anybody having syntax errors? Please stop me. So when you run it, hopefully you get 5 numbers that are valid numbers, but then you may see some garbage. To fix that garbage so that it doesn't have that garbage, and what do I mean by garbage? These values. This is negative 8 million or whatever, 8 billion. That's no good to us. We want to fill it with zeros instead. So what you do is where we declare our array, the int ia line, do this. Int ia is equal to 0. Like that. Now when you run it, you'll see that the first 5 data values are valid and the rest of them are 0. Well, that's better behaved than leaving that negative 8 billion in there. So this is a declarator or an initializer. Forget which term this book uses. We initialize the array to be 0. We all good? All right. So a for loop to step through the array. This one doesn't print it out. Instead, it sets every value of the array equal to 99. Why? I don't know. You could have set every value of the array equal to 0 if you didn't have that initializer thing that we did. So for count is equal to 0, while count is less than the array size, add to the counter, numbers at that subscript at that index is equal to 99. So by the time this code is done, every element in the numbers array will now equal 99. Alrighty, so if you define an array as a global variable, all of the elements are initialized to 0. If you define an array as a local variable, all the elements are uninitialized, and you wind up with those negative 8 billions or whatever else happens to be. Now that negative 8 billion, the debug version of the compiler is providing. If you ran it in release mode, you would not know what those values were going to be. They do that so that while you're running in debug mode, if you print something out and you see that negative 8 billion, whatever, you know, oh gee, that's uninitialized memory. I shouldn't have, used that. But you wouldn't see that same value. It would essentially be a random piece of data if you compiled for release mode. Now, whoever made the decision that global arrays do get initialized to 0 and local arrays do not was crazy in my opinion, but at least it's easy to fix. for us. If you always do that, then you know that the array gets wiped out and full of zeros. So I think that's a good thing to do. There is no bounds checking in C++, meaning that if you write past the end of the array, you have a problem. Let's do that. Right down here we had 3 names. Let's add a 4th name. Names C++ is equal to Tammy. So right, this one's 0, this one's 1, this one's 2, this one's 3. We have 4 elements now in an array that's only designed to hold 3. We are writing past the end of the array. The array had a certain number of bytes in it, and we've gone right past the end of those bytes. This is hopefully going to produce an error message. In the worst case, you get data corruption without getting an error message. And that's actually very common in C++. Some languages like Java and Python are really quick to pounce on you when you do this. They generate an exception right away. In this language, in C and in C++, it goes ahead and does it, and then you get to find out what happens later. I'm going to run it now. Boom. It says unhandled exception, access violation, writing location, blah, 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 blah. Break when this exception type is thrown. I'm going to go ahead and continue. I'm going to continue. I'm going to continue. All right. It's like hosed. So let's stop that.
So it's supposed to blow up?
It's blew up because we are running it under the debugger mode. I'm going to press this red arrow here to stop it, and I'm going to try to recompile it for release. So where it says debug Win32, I'm going to flip this down to say release, and then I'm going to go over here to build and rebuild the project. It'll turn for a little while. Display some warnings. I'm not going to fix those warnings. Then I'm going to run it. Debug, start without debugging. Now we're running it as though we were not in a test environment in an IDE. It ran successfully. However, Windows eventually figured out that we wrote past the end of the array, that our program wrote into some memory that it wasn't supposed to. And so it says a problem caused the program to stop working correctly. Please close the program. So Windows caught our problem, but you don't always know that that's going to happen, that Windows will catch the error. Sometimes you get corrupted data. I'm going to try to demonstrate the corrupted data, and then we're going to be done for the day. You see here where we had an array full of ints? Let's declare 2 arrays in a row. Int y1, no, what am I doing? Int ta, and it's going to be 3 elements long, is all equal to zeros. Test A, and then int tb is all going to be equal to zeros. You know what? I'm not going to make them equal to 0. I'm going to make this one equal to 1, 2, 3. We're going to fill in the values of that array to 1, 2, 3. And we're going to fill in the values of this array to 4, 5, 6. Now I want loops that's going to print out those values. Same business. For int I is equal to 0, I is less than 3. I'm not defining a constant. I plus plus, cout, ta, subscript I, ndl. And then do the same thing for tb. So I'm just going to copy those 2 lines of code, paste them. No, that's not right. And change it to be tb element I. So I copied and pasted, and that's what I changed. So when it runs, it should print out 1, 2, 3, 4, 5, 6. I have that error up there about that 4th name. I need to fix that. I'm going to fix that just by changing number of names from 3 to 4, because we really are putting in 4 names. So I'm going to change that constant. So where it says constant num names, change that to 4. And go back down here and let's run it, and we should see it print out the numbers 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, let's change some elements inside of TA before we print them out. TA0 is equal to 1,000. TA1 is equal to 2,000. TA3, 2, is equal to 3,000. And let's say that we've forgotten that TA only has 3 elements, so TA3 is equal to 4,000. And I want to put itty-bitty messages here above these 2 printouts. Cout TA array, followed by /n, and then cout TB array, \n. Just so that I can see which array is which. Firstly, I'm gonna comment this mistake out, right? I want to see it run without error now that I've added some things. And what I should see is that the TA array has this consecutive values 1,000, 2,000, 3,000, while the TB array is untouched. So I need to rebuild it. I'm going to choose Build, Rebuild Solution. And if y'all are still compiling in debug mode, you're not going to see the same thing that I'm seeing up here. It'll catch it more quickly. So when I printed it out, TA array was 1,000, 2,000, 3,000. TB array was 4, 5, 6. Now I'm going to go in and make my mistake. I'm going to uncomment that line out, so we're trying to write a 4th element into a 3-element array. Watch what it does. Let's build it again. Rebuild project. Let's run it without debugging. Now somewhere it wrote that 4,000 out, but we don't know where. It's kind of a mystery to me. I thought that maybe it was going to corrupt the array that followed. We know that some data somewhere got corrupted, but Windows didn't catch it. It didn't shut the program down. We don't see what got corrupted. That's interesting. I'm going to change that 3 to 4. See if that breaks it. Nope. I'm going to change it to a 5. Or 550. Anyways, it should be unnerving to you that the program is happily overwriting something in its memory and you don't know what it's overwriting. So far it hasn't overwritten anything that stops the program from running, and it caused no visible damage, but it certainly could. That's why it's nice to test your program in debug mode. I'm going to switch back from release mode to debug mode. I'm going to rebuild my project, rebuild solution. I'm going to start it in the debugger. And it didn't catch the error. I give up. That should have caught it. I thought that debug mode would catch it. We saw it do so earlier. Didn't this time. Lecture over. Array errors are a big problem in C++ because they don't automatically get caught, unlike in Java and in Python, where it will immediately throw an exception.